Hi everyone, today we'll be discussing how your lab graph relates to Beer's law. Now in the last video, we created this graph from this set of data points, and I just said to trust me that concentration went on the x-axis and absorbance went on the y-axis. But why is that, and how can we know that for sure without someone telling you? Well, that's what I'm going to tell you in today's video. So to understand why absorbance is plotted on the y-axis and concentration on the x, we are going to compare Beer's law to the slope-intercept form of a line. Now, as a recap, the slope-intercept form of a line is y equals mx plus b, in which y is the dependent variable, which is what changes in response to x. X is the independent variable, that's what you can control. M is the slope, and b is the y-intercept. Now let's relate it to Beer's law, in which A is equal to epsilon times B times C. A is absorbance, epsilon is molar absorptivity, which is a constant, B is path length, which is also a constant, and C is concentration. Now, if we look at these two equations, we can compare it, and we see that both A and Y, it's Y is equal to and A is equal to. So we can see that absorbance is also a dependent variable, and absorbance is dependent on concentration. So therefore, absorbance goes on the y-axis, and these two are related. Same thing with concentration. We can see that concentration is what we change in the experiment. So it will go on the x-axis, and we can relate it in that equation there. So we've already shown that the absorbance corresponds to y and concentration corresponds to x. Now let's look at the slope. So we can see that these two equations correlate in the sense that m is equal to epsilon times b. Now that's great, but I really want to be able to define these variables independently of each other and not as a term together. So we have to figure out a way to separate them. Now that's where path length comes in. Now path length is literally how far a light will travel through the solution in a cuvette. So that means that if a cuvette is 1 centimeter wide, the light will pass through 1 centimeter of solution. And most standard cuvettes are actually made to have a 1 centimeter path length. And if the path length is different, it will always be specified. Otherwise, we are always going to assume that B is equal to 1. So here, if we plug that into our equation, we can see that M is equal to epsilon times 1, in which case anything times 1, it's just itself. So M is equal to epsilon. So we just figured out that the slope of the line is equal to epsilon. Now you might notice that in the slope-intercept form of a line, it also has the plus b term, but in Beer's law, there is no such thing here. So why is that? Well, in Beer's law predicts that absorbance should be 0 when concentration is 0. So if we plugged in 0 for concentration, we would see that anything times 0 is equal to 0. And therefore, when concentration is 0, absorbance is 0. But in reality, experimental measurements are never perfect. The trendline may have a non-zero y-intercept, and you can see this in the trendline equation that we made in our example. And this intercept does not mean that Beer's law is wrong. It just represents instrumental or experimental error. So you probably will have this in your experiment, and that is A-okay. Now let's go back to our original example and see if we can find our molar absorptivity from our trendline equation. So if we remember that the slope is equal to epsilon, then we can just see that epsilon is equal to 6,774.1, and remember the units, inverse molarity, inverse centimeters. And just a note, even if the trend line doesn't go through 0, like we have here, we have that b term in the slope-intercept form of a line, the y-intercept is just experimental noise, and it does not go into the calculation of epsilon. So remember that the slope is just epsilon, and you do not have to worry about any y-intercepts or making that work with your equation to find what epsilon is. It's simply just the slope of the trend line. Now, how does this help us? For an unknown solution, we can use the trendline equation after measuring absorbance to determine its concentration. So let's say we have this unknown solution of yellow dye. If we put it in the machine and ran and got the absorbance, then we could plug this absorbance back into our calibration curve trendline equation to determine this solution's concentration. Seems a little complicated, but it's not. Let's do an example. So let's say we have an unknown solution that had an absorbance of 0.241 taken at 435.5 nanometers, and it asks, what is this solution's concentration? So one thing to note that is of critical importance is that this wavelength is equal to the wavelength from the calibration curve in which we will use the trendline equation. If they were not the same wavelength, this would not be the right calibration curve for this example, and you could not plug the absorbance into that trend line. So you have to make sure that it is the same wavelength. So let's take our absorbance of 0.241, which is our Y value, and we're gonna say is equal to 6,700. And we are going to solve for X, which is our concentration. So that is our variable. So we're just gonna solve for this like we would any math equation and add to both sides. And then this will give us 0.2604 is equal to 6,774.1 X. And then we will divide both sides by 6,774.1. And then we will get X is equal to 3.844 times 10 to the negative fifth, and that is in molarity, because we can see here that concentration was in molarity, so make sure you add your units on. So now we found our unknown solution's concentration. Thanks so much for watching. Please comment below what topics you would like covered next, or let me know any questions you might have. Have a great day.